All right. Good afternoon and welcome everybody. It's a great pleasure to have you here this afternoon. My name is Stefan Conradi and I'm the managing partner of Bayesian USA. And with me here today is Dr. Lionel Jouffes, my friend and colleague, who's just flown in from France and who will be handling the second part of our presentation today, and who will also be hosting for the next 3 days here in Washington, D.C., the introductory BayesiaLab course. So thank you, Lionel, for coming. Thank you for joining us here today. So it is presumably fair to say that right here near Washington, D.C., we're very close to the epicenter of policymaking. There are presumably few other places on Earth where there are so many laws, edicts issued that have really a profound impact on our society, or actually all around the world. So one might be forgiven to think that here in Washington, we sit like in front of this giant control panel, kind of contemplating which policies we should possibly enact. And for instance, now here's an example, actually a highly controversial example, a diagram that shows presumably all the elements of Obamacare. And if you look at this mechanism, this model, really this analogy with this gigantic switchboard isn't so far-fetched, really. And honestly, I do find this very, very difficult to understand. I'm not Dr. Jonathan Gruber. He would probably be able to explain this completely, but I'm just a normal mortal, so we won't be diving into anything like this today. Rather, we will be dealing with this. Something much, much simpler, a problem domain that consists of 3 variables, and we will actually agonize over this for the better part of 2 hours. And I bet you, at the end of this, Dr. Gruber would also have a problem with some of the challenges that a simple model like this can pose. Even though I've mentioned Obamacare and Dr. Gruber, this is not meant as a kind of a bitching session on government and policies and everything that goes wrong with policymaking here in Washington, D.C. Rather, we want to kind of take a back to basics approach, looking at, well, what is the core of policymaking? Going back to the basics, what's policy analysis all about? And so let me just take you through the agenda for today, kind of how we'll take you through it. We'll start off talking about, well, what is policy analysis overall? And we'll talk about causal inference by experiment, causal inference by data, or from data plus theory. We'll actually spend a lot of time on that. And then we go into, well, how do we practically approach this? How do we practically go from observational data plus theory, and how do we identify and estimate effects? And for that, we'll go into, actually we'll take a step back, go into theory, introduce the potential outcomes framework, and then as we work through that, take some traditional estimation approaches with regression, for instance, and then proceed to go into directed acyclic graphs and Bayesian networks. And that's where Lionel will take over, and he will actually show you how we can take a Bayesian network model and use that to estimate causal effects. So that's basically the rundown for today. So let's start off with, well, what is policy analysis? And I simply Googled the topic. And then there's obviously lots of written about this. And descriptions, so here's one, or this was actually the very first description I found from, I think it was the International Association for Impact Assessment, and they say, impact assessment, simply defined, is the process of identifying the future consequences of a current or proposed action. seems fairly straightforward. The second one is actually a fairly recent paper by Adele and Weiland. It says, policy assessment seeks to inform decision makers by predicting and evaluating potential impacts of policy options. Also seems to be fairly straightforward. But if we had to really boil this down, really make this, condense this even further, I would say policy analysis about the fact that we must anticipate the consequences of actions not yet taken. Very, very simple statement, but actually rather puzzling. We're trying to say through policy analysis, we want to predict the future. So what does that mean? How do we get there? How can we anticipate the consequences of actions not yet taken? Well, what do we need? We need an oracle. We need something, a device, somebody who can say, okay, if you do this, that will be the outcome. An oracle, something that predicts the future. So obviously, we're not going to start smoking something and start to debate how we can predict the future, but rather we want to figure out how we can create an oracle, a plausible oracle. What is our oracle here? The oracle here is causal understanding. Because if we have a causal understanding, then we can make claims about the future. If we know how our mechanism works, hi, welcome. We can then proceed to forecast the consequences of our actions. So the challenge of policy analysis is thus that we need to find a mechanism that links the proposed action to a potential consequence. So we need to understand cause and effect. We need to be able to estimate the size, the magnitude of a causal effect, and we need to be able to use that causal effect to perform inference. And then once we have that, once we understand that mechanism, then we can predict what would happen if we were to perform an intervention along the lines of our proposed policy. So, but now the question is, now that we know what that oracle should look like, well, how do we get it? How do we get this? How do we obtain this oracle? How do we identify that mechanism that links the proposed action to the consequence? Well, one way to find causal effects is by experiments. And this really goes back to Galilei with his plane and the ball that rolled down the plane, and where he measured the times of how long it takes to the ball to reach the bottom, etc. So, if you will, you could almost call this the very origin of experimental science. So, why does it work? One reason why it works, because we have a pretty complete control over the domain. We have the angle, we have the size of the ball, we have environmental conditions, etc. So we can try things out. We can explicitly manipulate our domain and thus derive the causal effect. So, but how about if we don't have full control of our domain? Well, that has remained a big problem for a very long time. And it was actually Sir Ronald Fisher who made a massive contribution in that area, because he proposed that actually one way to work with experiments of which you don't have complete control over all covariates is to use randomization. So by using randomization, by randomizing a treatment assignment, we can actually remove the effects of covariates on the outcome, and thus really use this method, this approach, as a causal effect estimation method. So that was great, major breakthrough, and until today, that remains really the very gold standard for experiments. I mean, drug trials, etc. They all go back to this work of Sir Ronald. So, but experiments can't always be done. be it for cost reasons, be it for ethical reasons, be it for PR reasons, as Facebook found out recently. There are just many areas where we really cannot engage experiments, even though we all recognize if we have the opportunity to do an experiment to estimate causal effects, that's by far the best thing to do. So where does it leave us? What can we do now? Experiments aren't possible in all cases. So can you guess what this is? It's like a hockey stick. Any suggestions? No, it's not global warming, no? Google trend, yes, you're very close. This is the Google trend for Google queries for big data. Shouldn't surprise us. Big data is going through the roof, both in terms of public awareness, but then also in terms of the data that is available today. And we have bold claims in terms of big data. This is perhaps one of the oldest ones, where the editor-in-chief of Wired said, with enough data, the numbers speak for themselves. So I think a lot of people have great hopes that, hey, with big data, perhaps we can overcome the limitations of, or the absence of experiments. So does big data come to the rescue in our quest for replacing experimental data? A lot of people hope so. A lot of people still think so. But that is not the case. As it turns out, data alone cannot provide us with a way to establish causal effects. So that's really one of the clearest warnings we should point out in this session. Big data alone doesn't cut it. But the problem is, that's all we have in many circumstances. On a lot of domains, regardless of whether it's global warming or any social science, for the most part, we do have observational data. So how do we deal with this? How do we formally and correctly deal with this? And what comes to the rescue, really, is theory. Something that kind of we're maybe even tempted to forget as we talk about the prevalence of big data is we do need theory to help us understand what causal effects we can identify. So let me now point this out, and this kind of presents the overall structure of our talk this afternoon, kind of the process of how we can go about identifying causal effects, or I shouldn't just say identifying and estimating causal effects. And what you see here is actually a very clear sequence. First, we need theory, a theory that allows us to determine whether a causal effect is identifiable. And then, yes, if it can be identified, then we can proceed to estimation. And for that estimation, we can then use all the abundant observational or non-experimental data that we have. And then with that, between identification and estimation, then we can obtain our causal effect, and that's what we want. Once we have the causal effect, then we can predict what would happen if we were to intervene in our domain, etc. So let me just now be kind of more precise about the semantics. And establishing, identifying, estimating, they all also sound fairly similar, but I want to be very, very clear here. First, we talk about identification analysis, and that is about determining whether or not a causal effect can be established from the observed data. So that's where we require theory. We require a formal causal knowledge, a formal causal model, or at least a partial model that tells us, or in which we hypothesize about how the data was generated. And what is very important, these assumptions, this causal model needs to be justified with outside assumptions. Only from human expertise, from domain knowledge, we can take these assumptions. These assumptions cannot come from data. There are no tests, there are no statistical devices, algorithms that can help us figure this out. This comes purely from human knowledge about how a domain could potentially work. So, and this is really a key point here. If we do not have such causal assumptions, if we cannot justify a causal model, there is absolutely no way that we can compensate for that absence with modern big data techniques, fancy algorithms, more data, etc. We will really reach a dead end. And this is what researchers must recognize, that in not all cases in which we wish to have a causal effect, we are actually able to get it. So this is a very, very important point. So then so if we agree, if we can justify that a causal effect can be identified, then we can proceed and actually estimate it. And there are now a whole number of ways of how we can estimate it, get a quantity for the size of this effect. And we can use a regression, ordinary least squares estimation. We'll show an example for that. And then actually, in the second half of today's presentation, that's where we'll go into Bayesian networks, where we can use Bayesian networks as the estimation device. And we'll show you that actually works remarkably well, and in many ways makes the life of the researcher a lot easier. So, this may seem fairly straightforward, but interestingly, for the longest time throughout the 20th century, what we're proposing now would have been outrageous for most statisticians. There's this one quote that kind of always sticks out for me. This is actually not that old. Considerations of causality should be treated as they always have been in statistics, preferably not at all. Statisticians, or I could almost speak or claim that about all of science, for the longest time, they've been highly reluctant to accept anything that deals with causality outside the world of experiments. And so basically they said, okay, let's take causality outside experiments is metaphysical. It's kind of black magic. It's not real science. It's unscientific. And as opposed to that, Professor Pearl, who among many other things was also the inventor of Bayesian networks, he said, well, this is actually a very, very serious problem. And I'll just quote him verbatim: "I see no greater impediment to scientific progress than the prevailing practice of focusing all our mathematical resources on probabilistic and statistical inference while leaving causal considerations to the mercy of intuition and good judgment." So that he saw that as a problem, that we spend all this time on statistical tests and model building and trying out measurements and fits and so on. But he said, sort of causal considerations always ended up being an afterthought. And so he really, in many ways, or he was a key contributor to this movement that helped kind of push the exploration of causal inference in science. And the book here that we marked with police tape all over, that was really a seminal work in that regard, because what he achieved is, what he brought about is to mathematize causality in such a fashion that scientists could accept it as an approach that is really scientific, as opposed to something metaphysical. In a very similar context, actually somewhat earlier than most of Pearl's works, was a framework for understanding causality, and that became known as, actually it became known by numerous different names. Perhaps most commonly known it is as the potential outcomes framework, or the Rubin model, or the Niemann-Rubin model. And this, I think, has now become the most widely accepted definition of what a causal effect is. I think intuitively we all know what a cause and effect is and what a causal effect is. But mathematically, what's the exact quantity? What does that mean? And Rubin proposed that. And well, you have this quote in the paper that's in front of you, so I'm not just going to read it. Rather, what I'd like to do is show a little diagram that once we're through it, we'll probably say, duh, that's totally obvious. The situation here is we have this young lady at the beginning of this timeline, and she's got a headache. And now there are two potential actions she could take. She could take 2 aspirins, or she could drink a glass of water. And after taking the aspirins, perhaps an hour later or 2 hours later, then perhaps she recovers, achieves the outcome Y1, she's happy again, or perhaps associated with treatment T equals 0, drinking a glass of water, she may still have this headache. So, and the difference between those 2 states, between outcome Y1 and Y0, that would be our causal effect. So we could then reason, either we could attribute the absence of the headache to the healing power of aspirin, or we could reason the other way around. So the first way would be, given that I've taken the aspirin, my headache is now gone, or in the case I had not taken it, the counterfactual, had I taken aspirin, my headache would be gone now. And so we can go backwards and forwards through this, but the key point, as simple as it is looking at the difference between the 2 potential outcomes, the potential outcome of recovering from the headache or not. And formally defined, this would be the individual causal effect. So beyond the individual causal effect, we are very often interested in how a causal effect relates to a population. In this case, we often look at the average causal effect, which is then the expected value of outcome Y1 versus the expected value of outcome Y0. That sounds wonderfully straightforward, very, very simple, but there's one big issue with this, and that is, for any individual, we can only observe one outcome at a time. So if this lady took the aspirin, we'll never be able to know what would have happened had she not taken the aspirin. Or if she drank a glass of water, we will never know what would have happened had she taken the aspirin. So we can only observe one of the 2 outcomes, which is really very, very frustrating. Throws a major wrench in this line of reasoning. So let's think about what could we measure? Now, perhaps someone might naively propose, well, let's just look at groups of people. Let's look at those folks that took an aspirin, as opposed to those folks, different group of folks, who drank a glass of water. And let's ask them about the outcome. Let's compare the outcome, the average outcome here, versus the average outcome there. And let's look at the result, and let's look at the measure S, which we call the measure of association. So outcome given t equals 1 versus outcome given t equals 0. And you'll say, yeah, that's great. We can easily measure that. We can easily take the average outcome of all these folks. But that doesn't really help us because that just gives us association. It doesn't give us causation because actually these folks, they're all different. They have different characteristics. So our association S is not a measure of causation. It's just association. So, okay, we're stuck again. So this can be computed easily, but it's not causation. The way we can compute causation is highly theoretical, but we can't measure it because we can't observe both outcomes. So what can we do here? And this takes us back to Sir Ronald, who, by the way, was a lifelong smoker and who, for the longest time, disagreed with the fact that smoking causes cancer, so which I always find amusing, and I feel compelled to mention it because he's like the world's most famous statisticians, and he got this one important causal issue totally wrong. But let's go back to what he said in his seminal work about randomization and look at what he actually said that justified randomized experiments. What he said in there is that randomized experiments work because it removes any bias through the randomized treatment assignment. So outcome Y1, outcome Y0, they're jointly independent of the treatment assignment. And so we could perhaps think, would it be possible to take this line of reasoning and somehow apply that to observational studies? Could that somehow be brought together? Well, unfortunately, no. That's very rarely the case. That condition is almost never met in normal experiments. However, there is another version of it, if you will. It's conditional ignorability, which says ignorability, or which relates to ignorability given a specific value of a subgroup, given certain variables, and we call those variables X. So now the question is it possible to have the outcomes be jointly independent of the treatment assignment given variables X? This could be one or it could be multiple variables. Is that possible? Because if this were the case, then we could make the following link. If ignorability conditional on X were to hold, then we can make this statement, and we can say the average causal effect given X equals the association given X. And this is totally fascinating. I think this is mind-boggling, that we can kind of make that leap from association to causation under certain circumstances. And that is given variables X. Now the question is, what are those variables and how do we go about conditioning on them? And again, this is where assumptions come in. How do we select those variables? How do we know that these variables even exist? Again, it comes all back to what we know about the domain, what kinds of assumptions we can make. So, and this is kind of where we now switch into sort of the more practical side of today's presentation. Now we actually want to do this. How do we work through this in a real-world example? Everything so far was entirely theoretical. So what do we need to assume about a domain? And here is this domain. And this kind of triangular-looking problem domain, this will be with us for the rest of the afternoon. And what we're saying now, all the assumptions that are needed for identification, all of these assumptions will be made in the form of a directed acyclic graph. So everything will kind of look like this. It will consist of nodes and of arcs. And we can encode all the assumptions we need that will then allow us to figure out, can we identify this problem domain or not? Now, this is now my favorite diagram, and we'll go through various iterations of this. This may also look a lot better in the paper in front of you. But the point is, we start here at the very top, and this really should always be the first question as we explore a domain. Is it possible to conduct an experiment? Because if it is, then forget all this. Then go conduct the experiment. That's the gold standard. But if that's not possible, then we need to go down the path, kind of the red path that is highlighted, and we need to develop theory. And we need to collect observational data, non-experimental data. And then from that point, we can really go in two directions. The first path, I will now talk about in the next 15 minutes or so. We will specify a DAG, a directed acyclic graph. We will figure out under what conditions identification is possible. And then we will perform the estimation and actually figure out what the effect is. That's what I will do. And then later on, Lionel will show how we can kind of do all this kind of rolled up into a more compact approach with Bayesian network. And there will be then two variants that he will explain in some detail. So, but now, for the next 15, 20 minutes or so, we will follow this path. So, what is a DAG? What is a directed acyclic graph? Well, a directed acyclic graph really has three elements, and only two of these elements we can actually see. The first element is a node, and that represents a variable in the domain. And what's important here, that nodes can represent observable and non-observable variables. And that's important to remember because we need to be very aware of potential unobservable observable variables. The fact that we can measure them doesn't mean they should not be included in the model. Then the second element is the directed arc that represents a possible potential causal effect. And the direction of the arc reflects the direction of the cause. So if the arc goes from A to B, means A causes B. And the third element here is perhaps the strongest statement that a DAG makes, and those are the missing arcs, the arcs that do not exist between nodes. That actually means there is no direct causal effect. There is an absence effect. We know that for sure. So that's perhaps the single strongest statement, the single strongest assumption that we need to make into a directed acyclic graph. Now, of all the directed acyclic graphs that we could consider, we can break them down into basic structures. As if we disassemble them, we could find, or any structure would fit into one of these three categories. The first one is an indirect connection. In this case, A causes B via C, perhaps the easiest one. Then we have the second class. We have connections. We have C as a common cause of A and B. And then finally, we have the common effect, which means C is the common effect of A and B. Again, looks quite simple, but now I'd like you to really pay attention because there are tons of implications from these structures. And we really need to be very much aware of these structures because it has numerous implications in terms of association and causation. So let's now look at those in greater detail. First one, the indirect connection. A causes B via C. What does it mean for association? It means that given or without setting evidence on C, A and B are dependent. So if I were to observe A, given the observation of A, I could make inference of node B. But once I set hard evidence on C, I would be blocking the path. So regardless of what I do to A, it would not be able to transmit the information across C to B. So by setting evidence, I would block that path. And we'll be talking about this blocking and unblocking quite a bit. This is really very central to our whole approach of using directed acyclic graphs. Similarly here we have C as a common cause of A and B. And this means if we find a structure for association, this means that A and B are marginally dependent. And if we condition, if we set evidence, if we observe the common cause C, the path is blocked and they can no longer provide information for each other. So that's the second one. And it's actually, in its behavior, quite similar to the first one. And now this one is different, the common effect. And this means C has two causes A and B. And here the behavior is just the reverse. This means marginally, A and B are independent, and the flow of information between A and B is blocked. So however, if we were to condition on C, we would unblock the path, information would flow, and they would become dependent. And this is very important, this conceptual understanding, as we later analyze structures and try to find, well, where does information flow? Where are associations? And by understanding these structures, we can then apply this to more complex networks and then see what's associated, what's not associated, what is conditionally associated, etc. So perhaps in the abstract, it's really not, it doesn't make all that much sense or may not be so intuitive. So let's go to an example. And this example will now be with us for the rest of the afternoon. This is the example of Simpson's paradox. Who's heard of Simpson's paradox? Show of hands. A few folks. Very good. And this is really a problem that pops up over and over again. It's kind of scary. It's a well-known problem, been known for over 100 years. I forgot when it was first mentioned as such. And really what this is all about is how an incorrect interpretation of association can produce bias. And when we talk about bias, or at least it's my intuitive sort of connotation of bias, when I hear bias, then I sort of think like, oh, it's a little off. It's not quite on target, but still going the right direction. But what we'll see here, that bias can be catastrophic and can lead to devastating results. So let's go to this example. Let's actually create a narrative about Simpson's paradox. I don't know what the original Simpson's paradox example was, but it was very similar to this one. And the story goes like this. We have a disease, and this disease equally applies to men and women. And an observational study is conducted, and that study finds that for those who are treated, they have a higher recovery rate than those who are not treated. This is this first table here. It says treatment yes means patient recovered yes goes to 50% versus treatment equals no, where the recovery rate was just 40%. So it's like, wow, this seems to work. Certainly going in the right direction here. More given treatment, more people recover. But then we take another step here and say, well, perhaps we can differentiate by male versus female. And now split this up in a new table. But now when we compare the treated versus the not treated, our recovery rate decreases. Given treatment, now we have, for men, 60% recovery rate instead of 70, and for women, a 20% recovery rate as opposed to a 30% recovery rate. Well, how is that possible? It seems to be entirely contradictory. And yet, both of these tables are entirely true. Both are entirely correct. And yet, it appears like a paradox. So what explains this paradox? The explanation is or comes from the fact that there was actually an unequal application of the treatment. In this particular case, I think it was like 70% of the male treatments received the treatment and only 25% of the female patients. We perhaps had some sort of self-selection. Perhaps there were more side effects for women, or you could imagine any kind of story that would explain that, but we very often have that in the real world, that people self-select for treatment. Okay, so that explains that. It explains why the outcome could be so different. So, but what is the real one? Is this now a useful drug? Is this a useful treatment? Does this heal people, or does it potentially kill people? So the way we're going to resolve that is with a DAG, with a directed acyclic graph of Simpson's paradox. So, and the way we set this up, we have one node for gender. Node x1 is gender. Node x2 is treatment. And node x3 is outcome. And we've kept this very simple. These are all just binary variables. Gender 1 is male, 0 is female. For x2, 1 is treatment yes, 0 is treatment no. And for x3, 1 has recovered, 0 has not recovered. So we just have a bunch of binary variables. And the way we've drawn the arcs here is we've drawn an arc from gender to outcome, because it appears that we have male versus females recover at different rates, give a different base rate of recovery. Then we have an arc that goes from gender to treatment, because apparently there's a self-selection. Given that you're male, it appears to be that you're more likely to receive treatment or seek treatment. And then finally, we have the arc that goes from treatment to outcome. That's the actual causal effect we're interested in. We want to know, if you take this drug, will you be more likely to recover? So that's what we want to find out. Now, yes, this is actually the principal point of the slide. If we now look at this DAG that we just have drawn, and Lionel will actually later on show you how to draw this within BayesiaLab. Here we're just showing it in this PowerPoint slide. We actually find that we have all three structures present in this DAG. The first one is an indirect effect, and we can look at gender via treatment to outcome. So the indirect effect goes via treatment. Then we can have a common cause. So here in this case, or let's perhaps look at the common effect. Well, it really doesn't matter in which sequence we look at this. Here, a common effect is x3 is an effect of x1 and x2. And then if we look at a common cause, x3 and x2 have x1 as a common cause. So all the three basic structures are already present here in this very simple DAG. Now, beyond these structures that we've just identified or just described, we're now introducing a new concept, and that's the concept of a path. And the fairly technical description is that in a DAG, a path is a sequence of non-intersecting adjacent arcs, regardless of their direction. And there are two types of paths. One is a causal path, and it can be any path that goes from the cause to the effect, in which all the arcs go in the same direction. And a non-causal path is any path between cause and effect in which at least one arc goes the opposite direction. And so we can now look at our DAG, look at all the paths that exist between what we would like to consider cause and effect. And we can then say, okay, this is the causal versus that's non-causal path. The reason why we're introducing paths is that paths can help us understand whether we can identify a causal effect. Because understanding the paths allow us to separate causation from association. And I'm now just simply stating a criterion, and we could just talk about this for quite a long time. But this criterion, this formal criterion, allows us to separate association from causation. And the way we do that is if we have a DAG and we can block all the non-causal paths while we leave all the causal paths open, then we can estimate the causal effect for that causal path. So if we can do that, and that's the adjustment criterion, and there are many other criteria available, the backdoor, the front door criterion, and so on. We will not go into all those, but we'll simply talk about this adjustment criterion. We want to keep the causal paths open while blocking the non-causal paths. So let's apply this to our DAG of Simpson's paradox. So what's the non-causal path in here? I've highlighted it here in pink. Our non-causal path is between treatment, going to gender, going to outcome. So why is it a non-causal path? Because we have the arcs go in opposite direction between cause and effect. Here we're obviously interested in cause and effect being treatment and outcome respectively. So the first path here is the non-causal path. Very obviously, the causal path here is the direct path between treatment and outcome. That's really the path that is of principal interest to us. That's what we want to find out. We want to know what that is, how strong that is, so we can say this drug, this therapy heals people or it kills people. And the objective of the adjustment criterion is that we want to keep this causal path open and block this non-causal path. Because if we were able to do that, then we could take the association that we can measure in the data and take the association between x2 and x3 as the causal effect. So basically what we're trying to do is we try to figure out a strategy that allows us to take the association from data and then interpret it as causation. And the adjustment criterion tells us what we need to do to get there. So I've just used the term adjustment. Well, what does adjustment mean? It's actually a very broad concept. It can mean the same thing as controlling, stratifying, setting evidence, observing, matching. It actually covers a whole range of techniques, of which we'll actually be using several throughout the rest of this presentation. And so actually adjusting for or conditioning, those are actually interchangeable concepts. We can, throughout the presentation, I try to focus on just using the word adjusting, but controlling really means the same thing. So thinking about this adjustment criterion, now given that criterion and given our model, which node requires adjustment? So we know we need to block the non-causal path. So here in the top, DAG. And now the first question is we need to block it. Well, do we need to block it? Is that marginally connected or not? And that's, just you may remember 5 minutes ago, we talked about the different structures and said an indirect connection is marginally dependent. A common cause is marginally dependent, and a common effect is marginally independent. So now if we remember that, we can look at this here and say, well, X1 gender, that's a common cause, that is marginally connected, so that's open. So if we take this network, if we take this DAG, there is information flow from treatment via gender to outcome. And that's what we need to block. We need to block that association in order to get to this one here. So by marginally, this non-causal path is open, which we need to fix. And then secondly, we have the causal path, this direct path here. And there's nothing on this path, so it can't be blocked. It has to be open. So there we don't need to do anything. So now we just need to make sure this stays as it is. That one needs to be blocked. And if we do that, then we're in business. Then we can just take the association from our data and basically read out the causal effect. So how can we adjust? How can we block this? And a very simple way of doing this is using the linear regression. And yeah, adjusting is really remarkably simple. We just need to include that variable of interest in the right-hand side of the equation. And in this case, x1. So I just say write x3 as a function of x1 and x2. x2 is the effect that I'm interested in, or rather beta 2 is the causal effect that I wish to estimate. But if I include x1 in here, by including, I adjust. By adjusting, I block the path. I block the non-causal information, and I can then estimate. So if I take this regression, I can compute the coefficients, and the one we're interested in here is beta 2 is minus 0.1. Okay, we're done. We have the causal effect. What's the problem? Well, duh, we just found out that we're killing people with this treatment, because our naive association said people are recovering. They're even taking the drug, they're improving. But once we apply theory to this, once we remove the spurious association, we get the opposite effect. And that's the problem. That's why this is known as the paradox, because it can introduce catastrophic bias. So from the association, the naive estimator of association, S, which gives us a result of 0.1, we go to a negative causal effect, negative average causal effect of minus 0.1. And so we have a reversal of sign, which really kills our intuitive interpretation of, actually not just interpretation, in this case it kills people. So, and why this is so important is that this is still happening so often in practice that Simpson's paradox rears its ugly head and ruins the intuitive interpretation of data. And as you could see, it actually took quite a bit of effort to resolve it, to really figure out what is the correct result given the data we have. So, and actually, you saw we took sort of multiple steps. We had to identify and then we had to estimate. As we now proceed into the second half of this presentation, we'll show how we can make a lot of this quite a bit easier by embracing the framework of Bayesian networks. Now, we haven't invented Bayesian networks. I've mentioned Professor Judea Pearl a little bit earlier, as he was complaining about the absence of causal thinking in statistics. One of his lifetime achievements beyond his research in causality is his invention of Bayesian networks as a framework for probabilistic reasoning for inference. And since he wrote his first paper on that topic in the mid-1980s, Bayesian networks have really evolved as a large field of study and have become very popular in academia. And one of our missions, it is to now promote Bayesian networks into broader research, into application, application by policymakers, and using Bayesian networks for policy analysis, for impact assessment, because as we'll see, in many ways, Bayesian networks can make the life of the researcher a lot easier, can kind of bring together a lot of the theory and the estimation, and kind of avoid what we did in the earlier example, where we had to go step by step and separately look at identification, estimation. Here, within Bayesian networks, we can do that in a more compact and an easier format. So what is a Bayesian network? It actually looks exactly the same as a DAG. But except the DAG is just a qualitative representation. The DAG just says x1 and x2. x1 causes x2, x2 causes x3, x1 causes x3. It doesn't say anything else. It doesn't say how or how strong, whether it's linear. It doesn't say anything of that. It just says that there is a possible causal relationship. Now, the way a Bayesian network evolves beyond that is it actually puts numbers behind it. So instead of just saying x2 causes x3, in a Bayesian network, we find actually conditional probability tables that exactly define that relationship actually between all the nodes. So we not only use this kind of as a sketch, as a kind of as a qualitative structure, but we can actually use a Bayesian network as a computation device, as an inference engine. And that's what I think really makes those so attractive. So here's my favorite diagram again. So we've now just gone down this path. We've gone from developing theory, observational data, collecting observational data. We've specified a DAG, said it's possible to identify, and then we used a parametric approach. We used a linear regression then to affect our estimate, to estimate our effect, and was negative as it turns out. So now we want to do the same thing, but in a slightly different way. And whereas in the left path here, you saw this very distinct approach. We first took theory and then brought data into play for the effect estimation. Now, by generating a Bayesian network, we actually kind of roll that almost into one. We generate a Bayesian network in one step, and then we have multiple approaches for estimating effects. And there we actually have multiple options. And Lionel will speak about what is known as graph surgery. And then secondly, he will talk about likelihood matching. And it's just not any likelihood matching. This is Dr. Lionel Jouff's likelihood matching. This is actually the algorithm that he invented, so you'll hear from the horse's mouth about how this works. And I think this is, for me, having worked in this field, this is really one of the most exciting innovations in this particular field because we can, all the steps we take, we still need the theory, but we can simplify a lot of the individual steps and get to our inference much more easily. So, having said that, I think it's time to switch microphones. And as we now switch into the second half, we will also go from theory into practice. And the way we show this practical application is by means of our software BayesiaLab. And that's obviously what we're very keen to promote. BayesiaLab is a software platform that allows you to machine learn Bayesian networks, to edit them, to perform inference, to simulate, to analyze, etc. So in a way, it's a one-stop shop research platform that can be used for the types of studies we've just done. And how this works on Simpson's paradox, this is what Lionel will now show you.
Oops. Thank you. Okay. Thank you, Stefan. So let's do some practice here with BayesiaLab. So I don't know if you're familiar with the software. I know some of you are. And so I will just create from scratch the network, the DAG, right? Just to represent the Simpson paradox. So in order to do so, you just have to create a new graph here. And we will first create one node for gender. So this is coming from our theory. So this is our knowledge right now. So I will just a little bit. So here we just have to say this is x1, gender. Oops, not used to this keyword. Right. Then, so this is our first dimension. Then we will create a second one. This is a treatment. So we can treatment. Okay, and we know that there is a causal link between these two dimensions, or at least this is our hypothesis, right? So we are speculating that people are taking the treatment and there is a bias in the selection. So we will just add a link from gender to treatment. And when we do that by using our expert knowledge, usually it's a causal link, right? Because Stefan said that Bayesian network was a directed acyclic graph, so this is true, but a directed acyclic graph is not necessarily a causal graph. Right? So when we are learning from data, we can find some relationship, and these relationships are just associations. Right? But in this case, this is a causal relation. And then we just need to create the last one, which is x3, and it was outcome. Right? And we create a link from gender to outcome and from treatment to outcome. So now we have our qualitative hypothesis. This is our expert knowledge. So this can be useful for identification, as we said before, for even if we want to use regression for quantifying the effect of treatment over outcome. But then, in a Bayesian network, this part is just the qualitative one, and this is the first one. And then we have another one, which is the parametric part, where we will associate probabilities to each node. Right? So for this node, gender, as there is no incoming links, this is what we call a root node. and then it will just be a marginal probability distribution, right? So we need to edit this dimension, and then we have two states by default. The first one is male, and the second one female, right? So we have this random variable now, and we need to define the distribution of this. So we would just choose, let's suppose we have in mind exactly what is the data, right? So we know that we have 50% of male in this study and 50% of female. We have this in mind, right? So now, as you can see, we don't have any warning signs anymore. Then we have this link from gender to treatment, which means that we are just specifying now that we want to have a conditional probability of x2 given x1. So we want to know what is the probability distribution of x2 treatment given male and female. So we just have to edit this. So treatment can be false and true, it's okay. And as Stefan said, we know that there is a bias, a selection bias here. That 75% of the male chose to use the treatment. So 25 here and complete. This is just a way to specify that given that we are observing a male, we know that there is 25% of chance that he did not take the treatment, right? And for female, this is the reverse. 75, 25, right? So now we have a marginal probability distribution for gender, a conditional one for treatment, right? And we just need to define this one, outcome. And this one has two incoming links, which means that we will have to describe the probability distribution of outcome given gender and given treatment, right? So we have a bigger table here. So treatment will be did not recover or recover. Okay. And here, for male, when you are not, for male that are not taking the treatment, there is 70% of chance to recover, right? So if I remember the data correctly. And when they are taking the treatment, it's 60%. And for female, it's 30% and 20%, right? Just have to complete this. And now, so I've just choose a kind of, I have the observational data set in my mind. I have my theory with respect to the selection bias. And then I've just designed by the network with this DAG, right? And given that I have these parameters, now, as you can see, I don't have any more warning signs, which means that I have defined my Bayesian network totally, right? So I have the qualitative part plus the parametrical part. And now I can use this as an inference engine, right? So I can go into validation mode and use this model in order to do inference, right? So I just have to double-click on these nodes to create what we call the monitors, these ones. And then I will be able to interact with this model to compute probability distributions. Because this is indeed a representation of the joint probability distribution of this small world. So we have a world with 3 dimensions, so we have just a cube, which is really simple here. And usually a Bayesian network is a compact representation of this hypercube. But in this very particular case, there is no, we are not compacting anything because this is the exact representation of the joint. So this is a theoretical representation of the joint. There is no missing links here, right? So we have a joint. And then based on this joint, we can compute all the probabilities we want, right? So we can do, let's suppose I don't know anything about, I don't know if there is gender has an impact. I'm just focusing on data. And it was the very first example Stefan took. If I want to naively see what is the effect of treatment on outcome, I will just compare treatment equal false. And I can see that the outcome is 40% of recovery with treatment equal true. And then we can see that there is a plus 10%. So if we don't know that there is this variable, we will take the wrong decision, right? So if we just focus on treatment, compare treatment equal true and false, we can see that setting treatment to true increase the rate of recovery, right? And this is what we have in the data set, right? But I will bring back gender. Struggling, there is no shortcut here. What happened here is if I set treatment equal to false, I'm changing the priority of gender, right? Because the inference in the Bayesian networks is, it does not depend on the orientation of the links. Well, just for sure, right? So if I set evidence on X2 in treatment, then I'm changing the priority distribution of gender and then changing the priority of outcome. So setting treatment, there is two paths, and this is exactly what Stefan showed you before. And we can also do that. So I will just define outcome as my target variable. Make a right click on this one. Where is my network? Good. Disappear. Okay. Bear with me. So I will directly go to the second phase and come back. Now I will take the data, right? So I have the same data set, but this time I will not build the network by hand, otherwise I will lose 5 minutes. So I'm opening a data set, this one. So it's a compact data set because I'm using weights, right? So you can either use weight or directly have thousands of observations. So here I have weights. So I'm going to use that, and we can see that we have one column for gender, another one for treatment, and another one for the outcome with the different states, and here how many occurrences we have for each combination, right? So just next. And then we have, so when we have a data set like that, BayesiaLab is able to create automatically the dimensions, right? And I can even learn the network in this case. I can machine learn the structure. So this is what I'm going to do. Learning. This is what we call unsupervised learning. And here it is. So by using machine learning, we were able to directly recover the structure, right? And as you can see, the links are in the correct direction, but it's just because gender was first declared, and then treatment, and then outcome. If I change the order of the column, I can have the link in the other direction, right? Because by just using this data set, without any expert knowledge, we cannot find if it's gender treatment or treatment gender and so on. So all these graphs are absolutely equivalent. Right? But well, this being said, so we found the structure. If I double click on the nodes, we have the priority distributions, marginal, conditional, and the outcome, right? And then I was just there. So we have our monitor. So if I say no, yes, I have the same output, right? And I was just trying to show you that if I define this node as a target node, I will be able to use a tool that will directly show you what are the paths that we use in order to propagate information, right? So if I click on treatment and go to analysis visual, I can use this tool, influence path to target. And then instead of, you have to know the rules, with the common effect, common cause, and so on. But it's really easy when you have 3 nodes, but when you have 50 or hundreds of nodes, it's just impossible to compute the path, right? So this tool will directly allows you to have the path. So you have, for this one, we know that there are two paths from treatment to outcome, one causal one and one non-causal. So if I click on the first one, causal, you can see that this is treatment outcome. Right? If I click on this one, I have another one that is non-causal, from treatment to gender, gender to outcome. So setting treatment to true, I know that there are 75% of men, and so on. And then this will change the outcome. So then we know that we need, if we need to, yeah?
So can you say more about how the machine learning
So what I just said is, by using the data set, we are not able to find if it's gender treatment or treatment gender. Here, in this case, it was a default orientation, because this is X1 gender, X2 treatment, X3 outcome. So we know that there is a relationship from these two, and this one being named X1 and this one X2, then by default, this is a heuristic. We're taking the first column and setting the orientation based on the data set declaration. Okay? But to tell the truth, if I go there, analysis visual, and show the ages, here, you can set the orientation in all the directions. So if we just, from a Bayesian network point of view, if I set the orientation treatment, gender, gender, outcome, or outcome, gender, outcome, treatment, everything is equivalent. So we cannot select one network just by looking at the data. We know that we have a triangle, but then we don't know if it's X1, X2, X2, X3, or X3, X2, X2, X1.
But X2, X3 is putting it as a causal.
So BayesiaLab will never tell you that this is a causal link. This is your job. As an analyst, you have to say, oh, given my knowledge, so the software found a link from X1 to X2, so there is a relationship, and I know, because you know that from the theory, or just because you know that it appears at time step T0 and the other one at time step T1, so given times, you can also sometimes set orientation. Okay? But here for this one, this tool just tells you that there is no orientation from a Bayesian network point of view. We are using what we call the minimum description length algorithm. So we are trying to reduce the entropy, the entropy of the system. So each node has uncertainty. We are measuring the uncertainty of the node by using entropy, and we are trying to add links to reduce conditional entropies. Okay? So we know that we have two paths, right? And then if we want to estimate the effect of treatment on outcome, given that this is our causal graph that we said it was causal, right? So it's not automatic. We need to block the information that goes from treatment to gender, right? So this is what Stefan did with regression, just putting gender in the formula, right? So I will show you how you can do that with a Bayesian network. And there are different ways to do that. And I will start with a tedious one, right? So the first one that you will be able to find in some papers is to say, okay, we need to create, so I will remove it, I will do that. So I want to need to measure what will be the impact of not just observing treatment equal yes or true, but I want to see what is the impact of doing the treatment. So now I will give you aspirin, or I will give you the treatment they have. And you will not freely choose it, right? So I will create a node, do treatment. And in this case, with just two states, true or false, and we don't care, just 50-50, right? Because this will be a decision. And I will add a link from treatment, from do treatment to treatment, right? And now I have a warning because I'm changing the probability distribution of treatment. So I need to define what will be now this. And indeed, it's more, I will do it really as you have to do it. So you need 3 states here. Oops. So which is here when you do, FC is when you are not doing anything. So you are just using the observation, right? And then usually what we do is just saying that there is 1 here and 50-50. So we're just normalizing this, right? And this will be, so I'm just changing, trying to increase the size of this. This is working, yeah. So now FC is for, I'm using the observational data. So I will just say, okay, this is the exact same thing as this one. Right? But this, I'm removing. And I will say that if I decide not to give the treatment, then no will be equal to 100, right? And if I decide to apply, to give the treatment, it will be 0. Okay. So I have this new graph. And I want to compute what is the total effect or the effect of treatment, this one. And if we come back to this, so this is our target, our action, the treatment, and gender. And I will compute the path here. Visual. Oops. And as you can see, now I just have one path from do treatment to outcome. Right? Just because, if you remember, there is what we call V structure here, a collider, and then there is no impact. Gender and do treatment are marginally independent. So if I set evidence on do treatment, if I say, well, it's false, treatment is equal to no, for sure. But as you can see, there is no impact at all on gender. Right? And then I can measure that recovering is, just let me, so I have a 50% of chance to recover, and do treatment true, 40%. So now I have the true causal effect. Right? It's not mixed with gender. Okay? So just by adding this node. Well, when I said just by adding this node is, it took 5 minutes just with 3 nodes. So let's suppose you have a big network with lots of decisions. If you have to create extra nodes like that for each decision, it can be tedious, right? But well, this is one way to do that. So let's come back to the other one. Another one will be just to, I will copy this graph again. So we still have to block the information flow from treatment to gender, right? So one thing we can do is, just I will copy this, is just to do what we call a graph surgery, a mutilation of the graph. In order to prevent any information going from treatment to gender, I can just remove the link, right? And then set this back. And if I do that, I can compute treatment equal false, 50%, true, 60% of recovery. 40% of recovery for yes, and 50% for no. We have the same causality. But as you can see here, my graph has been mutilated, right? So if I want to compute another impact of another decision, I will have to make copies and so on. So it will not be easy, right? So another way to do that is to directly go into BayesiaLab like that and say, well, treatment will, I don't want to just make an observation, because when I double click on no and yes here, I'm just setting 100% on people who did not take the treatment. Right? So I am observing in this data set, if you will, or in this joint priority distribution. So instead of just observing, what I can do is make a right click and say, I will not observe, I will intervene, right? So I'm selecting intervention. Then my node is blue, or the monitor is blue, just to indicate that this will be a decision now. And by setting treatment to no, there is an automatic surgery in the graph, right? And I have this 50% of recovery for no and 40% for yes. So I have the causal impact, right? If I remove this, my link is back. Right? So it's a much convenient way to mutilate the graph than just doing it by yourself. Right? And this is, well, what we call the Pearl graph surgery. And then there is the last one. So we'll come back into observation. This is a matching, right? So the likelihood matching. So what we can see here is if we set treatment to no, we are changing the population. So we are comparing two populations that are really different. One is made of 75% of male. The other one is made of 75% of female. Right? And male being less likely to die from this disease, we have a big bias. Right? So we have to come back in the framework of control experiment. And then we want to be able to say, well, I want to compare treatment equal no and treatment equal yes with the exact same population here, right? So instead of just removing the link and so on, we will directly find in the joint priority distribution what are the particles that are compatible with our observation. And then we want to say, when I will set treatment equal no and set treatment equal yes, I want to have a posterior priority distribution on gender equal to 50-50. Right? So in this case, I will just click on gender and say fix. So I don't want this probability distribution to change, right? And then I will set treatment equal to no. I still have my link. I did not modify the joint probability distribution. I've just changed the joint probability distribution, right? So I've selected a subpopulation in my joint probability distribution, in my cube here. And then I have the outcome, 50% for recovery, and here, 40% for recovery, right? And you can see that usually, so it's not just a graphical thing. When I do no here, you have the joint here. So the joint priority is 100%, which means that in my joint priority distribution, all the particles are compatible with my set of evidence, because I don't have any evidence. And if I set no, now my joint is just 50%, because I've selected 50% of my population, right? And you will see that when I'm fixing gender, setting treatment to no, it's not 50% anymore, it's just 25%. So we are really selecting the particles that are compatible with our evidence, right? So this is the last way to do that. And this is also perhaps more flexible than the surgery, because surgery is based on really a graphical causal graph, right? So we need to really have the link from gender to treatment, right? And as I told you before, you know, if you just are using a data set, learning the network, you can have this link from treatment to gender or gender to treatment. We will not be able to know that, right? So let's suppose it's the other way around here. I can make a right click and invert, and I have the exact same probability distribution, and I can do the exact same thing here. The results are absolutely identical, right? So now if I do surgery, So I want to intervene on treatment, not on gender. I will say no and yes, and now it's not working anymore, right? So I can see that treatment equal yes, 50% of recovery, no, 40%. So now I have a positive effect. And we know that this is not correct, just because with the surgery we are removing the incoming links. So we don't have any incoming links anymore with treatment now. So this is highly dependent on the graph. Whereas with gender, if I use likelihood matching, if I say I want to fix this, and I want to remove this, no equal 50, yes, 40. So it's still working here, because we don't care about the direction of the links, right? Just we care about the joint priority distribution. Okay? So this is more flexible in this way, right? So you don't need to really have the DAG, or at least you can have the DAG, a representation of the DAG in your mind, but use the DAG for the Bayesian network with links in the other direction if it helps you to save some parameters, not to have a big, very complex Bayesian network. So this was something I wanted to show you. And another thing is I will just associate, or no, I don't have to do that. We will see another tool that allows to compute direct effect and total effect. So we have a report here that allows to compute direct effect, right? And this tool is based on likelihood matching, right? So when we are computing the direct effect of gender, we are holding fixed the priority distribution of treatment, right? And when we are computing the direct effect of treatment, we are holding fixed the priority distribution of gender, right? And then we can see that the direct effect of gender is 0.4, so the exact same result we had with the regression, and minus 0.1 for treatment, right? So this is really what is, given that I'm increasing by 1 unit treatment while holding fixed gender, what is the impact on outcome? Okay. So this is, I will just make this. Okay. And this one, we have also another one, which is the total effect. So direct effect is always the effect of one node, given that you are fixing a defined set of nodes. So if you are not defining what we call non-confounders, we will hold fixed everything else, right? And we can also compute, this is here, the total effect. So this is almost the same tool, but now we are not holding fixed anything. So for this one, we have the total effect of gender is the effect, the direct effect of gender, 0.4 here, plus the effect that is going via treatment, right? Because here we still have two paths. If I go there. So if I'm interested in computing what is the total effect of gender, I have two causal paths. I have the first one, gender outcome, and the second one, gender treatment outcome, which is also a causal path, right? So if I want to compute the total effect, I knew it was not a good idea to use your computer. I'm lost. Okay. So now we have this one, and total effect of 0.35, which is this 0.4 plus the effect of between gender and treatment time the effect between treatment and outcome. Right? So we are decreasing the effect because we have this negative impact of treatment. So this, for genders, this makes sense, right? Because this is really a causal impact. But for treatment, this is not correct, because we come back with our positive effect of 0.1, because we are computing the effect of treatment outcome plus this one, right? So this is the reason why if we want to compute total effect, we need to fix some nodes or to use direct effect. Okay. We still have some time. Perhaps I can just go. I wanted just to show you another one. So this is a slightly more complex network where we have 3 actions, x1, z, and x2, 1 outcome, and y2, which is a descendant of y1. Right? So in this one, so we have coefficient here. So because everything is, so this is just a theoretical example in this case. So everything is binary. And then this is the exact same thing as a structural equation model, a linear structural equation model. Right? So we have the coefficient here, which means when I'm increasing by 1 unit x1, I'm increasing by 0.5 y1 if I hold fixed everything else. Right? So this is really a structural equation model. And I know that I will take back my total effect example here. If I want to, I don't know if you are familiar with the right path rules. We have, for example, in this case, if I want to compute the value, we have one direct impact from x1 to y1, which is 0.5. And the total effect of x1 in such linear structural equation models is just this 0.5 plus the weighted sum of all the other paths. So it will be plus 0.8 times 0.1 plus 0.8 times 0.8 times 0.2, which is 0.708. Right? Because we have 3 paths here. And for z, it will be 0.1 plus 0.8 times 0.2, but we have also this one, 0.8, 0.5. Right? So this is a way to really compute very easily the effect. And in this case, the exact same thing as with Pearson, with Simpson, this is only true for x1. And this is wrong also for y2, because y2 is the consequences of y1. Right? So this is only the total effect. This one is the only correct one. Right? So if I want to compute the direct effect, so I can use the same tool, and I will have the exact same coefficient here. I can show you report effect. So except that we don't have to care about this one, about y2, but otherwise you can see that. Oops. No, we cannot see. I have just to. I will set this node as a non-confounder. So setting this node as a non-confounder allows me to indicate to BayesiaLab that we will not fix this node, right? So I'm setting this node as a non-confounder, and now I will compute the direct effect. And we have, for each one, we can see that the direct effect of x1 is 0.5. This is this one. For z, it's 0.1, and for x2, it's 0.2. So we have this coefficient of the linear structural equation model correspond to the direct effect. Right? And the point I wanted to show you in this case is we have seen so far that we can use a DAG in order to know what we should control or not, right? But we also have to be careful about what we should not over-control, right? So we just have to keep in mind these coefficients. So we can see with direct effect we have them. And I will remove here y2 from the non-confounder, right? So now when I will compute the direct effect, I will also fix this one, right? And now you can see that the coefficients are not good anymore. So we have introduced a bias just because we have controlled y2. So when you are estimating a direct effect or causal effect of a variable toward an outcome, you should also be careful about what you are controlling. You cannot control any node that belong to the path from the treatment to the outcome. Since this is quite obvious, this one. But you don't have to control any descendant of the outcome too. Otherwise, there is a big bias, depending on the strength of the relation between y1 and y2. Okay. So this was one additional warning, and I would just want to conclude this small exercise. So this is a graph that we have seen with Felix, our co-author. And so this is, again, a pure theoretical network. So you have the treatment variable in green, the outcome, y, and we have other nodes, plus u, which is a hidden variable. So we know that we will never be able to measure this variable in our observational data. Right? And then the question is, well, let's suppose you have, so either you alone have defined this graph as a causal graph, or as a team you have defined it. Right? So for you, this is your hypothesis. This is how the data is generated. Right? And you have data for everything except this white node. And the question is, can you identify and then estimate the causal effect of treatment on y? So do you remember the rule? You have to let the information flow by using the causal path and block all the information that use the non-causal path. So in this case, we just have to go to analysis again, visual, inference path, and we can see that we have 3 paths from treatment to outcome, and only one causal one, treatment to C, C to Y. And then we have path 0, U, X, X treatment, and U, Y, and the other one, treatment X, X, Y. Right? So we know that now it's quite easy to estimate the causal effect of treatment on Y. We just have to block these 2 paths. And there is one control that will allow us to block these 2 paths altogether. We just have to control X, and then it's over. And I can just do that, make a right click, and say, I will fix that, and do my treatment again, my analysis, sorry. And now, given that I've set this evidence on X, so I've just indicated that I've controlled, I'm controlling X, and now I just have one path, which is a causal one. So now it's okay. I'm able to identify this causal effect, and then to use BayesiaLab to measure this. Okay?
Why isn't there a path to A?
What's that?
Why isn't there a path to A?
This one, because this is a collider. So with A, this is what we call a V structure. So B and treatment are marginally independent. They are common causes of A. So they become only dependent given a set of evidence on A or on one of the descendants of A. But as I'm not setting up any evidence on A, it's okay. But let's suppose I'm modifying this network. I'm adding a node here. And if I'm fixing this one, right? And if I now analyze, now I have this one. So it's going through A now. Because I set something here, so I'm opening the information flow via A.
You could see as well, right?
No, because C, if I set evidence on C, now I will bias the estimation because I will reduce information flow from treatment on these causal paths.
Since C only goes
Uh-huh.
know C, and you know you're doing good treatment on C, then you could estimate the causal effect out.
But why are you going to block this information path? You don't have.
Not possible. Not possible.
So?
I mean, estimate using C.
But you are using C, indeed. If you are not setting evidence here, the information will go via C. But the thing is, in order to estimate this effect, you don't have, you need to not to observe, not to control anything on this causal path. So you don't have to control this one, nor this one.
Right, I don't need to control it. I mean, use it.
But if you are using it as an estimate, or if you already know the parameters, you mean? As in my structural equation model example? Or?
C is not influenced by that.
No.
So you could also estimate the influence of people in C.
Yeah, but if you want just to estimate this, but this one, visual, and you will see that there is two non-causal paths too. Because this is going this way, so this is going via treatment. Sure. This was a very important point. This is the theory. So this is an assumption, your assumption or the assumption of your group. And then you have, but you cannot observe you. You, it's, yeah. And we will perhaps just conclude on this one, and you will see that with this kind of graph, the question is, can we, if this is, again, if this is the truth, can we estimate the treatment, the effect of treatment on Y? I will not spend 1 hour on this because it's not obvious, but so we just, again, can use the same thing, path. So we can see that we have two non-causal paths, only one direct one, and we have path 0 and path 1, right? So these two. So we can think about, oh, yeah, all these paths are going via Z1. So perhaps we can control Z1. So let's do that. I'm setting, so when I say I will control, I'm just fixing it just to have the impact on the path analysis. And now I have 3 non-causal paths, right? So I still have this one because this is a V structure. So before it was marginally independent, but given that I set an evidence on a collider, it's going via this path. I have this one. So now it's going via the hidden variable. So I know that I will never be able to control this one, right? And this last one. And then you can control this one too. And we will still have, there is no way indeed in this example to block non-causal paths. The only way would be to set evidence on this hidden variable, but as they are hidden, we cannot control them. So if this is the correct graph, you are screwed. So, yeah. Okay, so perhaps we'll hand over to Stefan for.
All right. Thank you very much, Lionel. I hope you found this useful, this demonstration with Bayesian networks. As you can see, even though we've just worked with fairly simple examples, 3 variables, with a handful of variables or a few more, it becomes very, very challenging to really identify whether a causal effect can be estimated. And as we keep saying over and over again, you need tons of theory to do that correctly. So if we just remember the very first diagram I showed of Obamacare with whatever 300 nodes that we had in there, if you can just imagine what it would take, what assumptions we would have in order to estimate causal effects. So I don't even want to go there. So we have a few more minutes. So this would be a great time if there were any questions. We could talk about those. No further questions. You all have in front of you a copy of one of our recent papers. In fact, the presentation we shared with you today was kind of a live version of that paper. So if you want to follow along each and every single step, it's all documented in this paper. Plus, you can also download a trial version of BayesiaLab. So you can replicate actually everything we showed you today within the framework of Bayesian networks. I think that's really the best way to become familiar with the framework of DAGs and Bayesian networks. And I would hope that you find this useful and practical for your own research work. So if we don't have any further questions, I would like to thank you very much for coming, for joining us here this afternoon. Please do feel free to reach out to us. All of our contact details are in the materials in front of you. And we will be back in the Washington area regularly for either workshops like this or also for our 3-day BayesiaLab course that goes into a lot more detail about how to use Bayesian networks for all kinds of research problems, well beyond causal inference, going into many other areas. And I see several of you who are in the audience actually have had a previous opportunity to join us in one of these courses. So with that, thanks again, and please do feel free to reach out to us with any further questions. Thank you.